Welcome to DVCon 2023. I'm Dabarshi Chatterjee, and today I'm going to present GraphCov, RTL graph-based test biasing for exploring Uncharted coverage landscape. This paper is co-authored by Spandan Kachadia, Chen Luo, Kumar Kushal, and Siddhant Dodi at NVIDIA Corporation. So coverage closure is undoubtedly one of the most tedious phases of design verification. Towards the end of the project, as we run more and more tests, the coverage numbers typically asymptotically converge to a number less than 100%. And let's say at the end of the project, we ran 2 million tests and we hit 98% coverage. Then at this point, running more random tests have very little incremental benefit in terms of gaining more coverage. So how do we really cover this last mile? The typical approach involves writing and running directed tests. We fix test bench bugs, and oftentimes we waive coverage conditions which are deemed less risky. And the question here that we want to ask is that can we move towards a more faster and automated coverage closure? So for this paper, whenever we're talking about coverage closure, we will mean functional coverage, which will be measured in the percentage of cover properties that were hit. So since we're going to talk about cover properties a lot, I would like to introduce at a high level what cover properties are. So let's suppose we have a dot and there is a block inside it, and the test bench, the verification owners are writing random tests to control the primary inputs, and the designers are interested to see if we exercise a condition which when the request was asserted that 5 clocks from the request assertion, the act came back within 1 or 5 clock. So if that's the property that we want to see getting covered, then this is the syntax to code that up. And once you code the cover property up, if after running a bunch of tests, that condition was hit, then we will get to know it. So if that cover property was hit, we will call it CCP, or covered cover property. If it was unhit, then we will call it UCP, or uncovered cover property. The overall coverage number is nothing but the total number of covered cover property as a fraction of the entire cover properties that were coded up. And the question that we want to ask in this paper is that at the end of the project, if there are a certain number of cover properties which were uncovered, then can we automatically hit or cover some of at least a fraction or set of those uncovered cover properties at the end of the project? So considerable previous work exists on accelerated coverage closure. In the interest of time, we won't be able to go over all the previous work that was detailed out in the paper. But we'll go over one interesting work called Design to Vec, which was presented by Shobha Vasudevan from Google Brain at NeurIPS 2021. So at a high level, what happens is when we change $value plus arg or $test plus arg, we change the nature of the tests, and the tests kind of hit various different cover points. So if we have the simulation data and know which all value plus arg actually hit which coverage, and we have a high-level abstraction of the RTL in the form of a control data flow graph, then we can use these two information to generate a GNN-based model, which will now predict what value of plus arg can hit what coverage. And if we have that kind of a model and we have a cover point which was never hit, we could try to figure out what combination of plus arg can possibly hit that cover point. So this is an example of an application of ML-based technique for coverage prediction and accelerated coverage closure. But like other methods, using ML has its own challenges. You need to keep the model updated with design changes, and learnings are not really transferable from one unit to another. So in this paper, we will present a simple heuristic for hitting a subset of the uncovered cover properties at the end of the project without training models with huge amount of data. In this slide, we're going to present the high-level overview of our method. So what we want to do here is to hit uncovered cover properties that have no precedence of being hit. And so since we do not know how to hit them, we turn our attentions to actually covered cover properties that meet 3 criteria. And one of the criteria that this cover property must have is that it should have a low hit rate compared to other CCPs in the design, which means that this covered cover property's neighborhood has been relatively less explored. And another property or criteria that this cover property should have is that it should have a large number of uncovered cover property in its neighborhood. And the covered cover property should also be closely tied to the UCPs in its neighborhood. Later on, we will explain what we mean by neighborhood, how do we quantify whether how closely tied a CCP is to the other UCPs in its neighborhood. But for now, the high-level idea is that we will assign score to the covered cover properties to measure how good the cover property is with respect to these criteria. And then we will call the CCP with the highest score as the target CP. And the high-level idea is that if we can bias a set of tests towards the target CP, then since this target CP's neighborhood is less explored and it has a lot of UCPs around it, and the UCPs are closely tied to the target CP, then by bumping up the hit rate to the target CP, we could possibly hit UCPs in its neighborhood. In order to define concepts such as neighborhood and association between two cover properties, we need to introduce the notion of a trace driver graph. And the trace driver graph is nothing but a high-level abstraction of the underlying RTL. So let's explain this with an example. So the code on the left is an RTL code, and the figure on the right is the trace driver representation of this RTL. Now, if you look at this RTL code carefully, you'll see that there are signals like Y, which is being driven by either Z or 1 on a pause edge of a clock, depending on what the value of X is. And then for this code, we want to figure out whether Y ever becomes 1. So we create a wire called W, and which becomes 1 when Y is 1. And we hook up that wire W to the TP input of the module SVT, which is implementing the cover property. Now, how does the trace driver graph look for this RTL? So we define the trace driver graph where each node is a CP or a signal. So for this RTL, we have signals such as X, Y, Z, and W, and we have the cover property CP1. So all of these becomes nodes in the trace driver graph. And the edge represent a driver or a guard condition for driver. So what that means is if you have an edge from a source to a destination, it means that the source is either a driver or a guard condition for the driver. So for instance, Y is being driven by Z. So we have an edge from Z to Y. And X is a guard condition for the driver for Y. So we also have an edge from X to Y. So this is how we create the trace driver graph representation from the RTL. And notice that we have ignored all constant operands and timing statements in this trace driver graph representation. And once we have this trace driver graph, we will use this to quantify notions such as neighborhood and association between cover properties, which will eventually help us assign scores to cover properties, which in turn will help us identify the target CP that we discussed earlier. This slide shows the picture of a trace driver graph of a real unit level design at NVIDIA. And the rendering has been done using a tool called Cytoscape. If you zoom in to the top right corner of the graph, then this is how it looks like. And you'll see that we have colored the trace driver graph with, and the nodes have been colored based on the type of nodes. So for instance, the gray nodes here represent signals, the red ones represent uncovered cover properties, and the green one represents the covered cover properties. And a darker shade of green represent higher hit rate to those cover properties compared to the lighter shade of green. Now that we have the trace driver graph representation of the RTL, we can now formally define what we mean by the n-hop neighborhood of a covered cover property. So we define the n-hop neighborhood of a covered cover property as a set of nodes which includes both signals and cover properties that can be reached within n consecutive hops starting from the CCP in the trace driver graph. Alternatively, you could think of this as if you load the design on the Verdi and you start and if you're allowed to make n clicks to either the trace load or the trace driver button starting from the covered cover property, then all the signals and the cover properties that you can reach by n consecutive clicks to trace load or trace driver button belongs to the n-hop neighborhood of the cover property. So this slide shows a visual representation of the 6-hop neighborhood of a sample a covered cover property. So the covered cover property is sitting here, and if you zoom in around the covered cover property, you will see some CCPs and some red UCPs around it. And the figure on the right shows the 6-hop neighborhood of the covered cover property, which is sitting somewhere here. So everything colored with yellow and blue here belong to the CCP, belong to the 6-hop neighborhood of the CCP, which is sitting here. Now you might ask that why are these guys why these guys do not belong to the neighborhood of the CCPs, although they are closer, while these nodes are farther but belong to the neighborhood of the CCP. And the reason is because although if you zoom in, it will be clear that these guys, although they have been rendered in this graph to be located farther from the CCP here, but from a hop distance perspective, they are actually closer than these guys. And the reason they are rendered farther is because they are closely associated with some of the nodes here. So that explains, that shows a visual representation of how the 6-hop neighborhood of a CCP looks like. Now that we have defined the concept of neighborhood, let me now present some interesting statistics which will shed some light on the intuition behind the GraphCov approach. So this is a scatter plot where every point is a CCP or a green node in the trace driver graph. The x-coordinate of the CCP represents the sum total of the hit count of all the CPs in the neighborhood of this CCP. And the y-coordinate represents the percentage of CPs in the neighborhood of this CCP that was hit. As you can imagine, points with higher x-coordinate in this scatter plot means are the points whose neighborhoods have been well explored. And the points with higher y-coordinate are the ones whose neighborhoods have been well covered. And since this scatter plot was generated out of end of project report, most of the points which have high coverage in its neighborhood are also the points which have high hit rate in its neighborhood. And there are some exceptions like these points which have high hit rate but our neighborhoods are not well covered. And the intent of the GraphCov approach is not to focus on these points, but the focus on points which are kind of located in this ellipse where the CCPs in this ellipse have relatively low hit count in this neighborhood and also have relatively low cover percentage in its neighborhood. And so the idea is that if we can somehow bias test towards these CCPs, then by increasing the hit count in the neighborhood of these CCPs, we might be able to boost the covered percentage around these CCPs and thereby hitting UCPs in its neighborhood. So how do we really go about identifying these CCPs where we could bias our test towards? And as we mentioned earlier, that at a high level, there are 3 criteria. One is that the CCP should have relatively low hit rate. And for that, we could just filter out CCPs that have high hit rate. But then there are 2 other criteria, such as the CCPs should have a lot of UCPs in its neighborhood, and also the CCP should be closely tied to the UCP in the neighborhood. And since these are 2 criteria, we have to combine them into a single formula and assign a score to CCP so that we can actually compare the CCPs based on the scores. So in this slide, we're going to explain at a high level what we mean by association between a CCP and a UCP pair. So we define association as the number of shared ancestors divided by the average distance of the UCP from the shared ancestor. So if we have, for a CCP UCP pair, if we have more shared ancestors, that means there is more association, and the less the distance of the UCP from the shared ancestor, the more the association. So and then finally we define the overall score as the sum of the associations of all the CCP-UCP pairs in the neighborhood of the CCP. So the figure on the right shows um, the n-hop neighborhood around two CCPs, C1 and C2. As you can see here, for this CCP-UCP pair U1, C1, there is only one shared ancestor, and the distance from the shared ancestor to the UCP is also 1. So the first term, A over D, for the score C1 is 1 over 1. And on this side, there is, between the C1 and U2 pair, there is also one shared ancestor, but the distance from the UCP from the shared ancestor is 2. So this term is 1 over 2. And overall, the score for C1 is 1.5. If you do the math here, you will see the score for C2 becomes 2.33. And as you can see, both C1 and C2 have the same number of UCPs around in its n-hop neighbor, but the score is basically saying that C2 is more closely tied to the UCPs in its neighborhood than C1. So we use these scores to compare CCPs to figure out how good they are in terms of those criteria that we mentioned. Now that we have all the bits and pieces discussed, let's put everything together and see how the overall GraphCov algorithm works. So the first step is to collect baseline coverage data by running regressions. So what we do here is we just run test on the GUT, we collect the coverage data, merge the coverage data, and create the final end of project coverage report. And this report contains information like which cover properties were hit and which were not hit, and what was the hit count for each of these cover properties. So next, we use the NPI commands provided as a part of the Verdi package to parse the RTL and create the signal source destination map. This has information about which signal is being driven by which other signals and so on. Once these two steps are done, we combine the information from these two steps to generate what we call a colored trace driver graph. And we showed one example of this trace driver graph in a previous slide. So after that, we move on to step 3, where we filter out the CCPs with high hit count and then use the formula for the score to assign scores to each of the low hit count CCP. So it would be the light green nodes in the TDG that get the score assigned to them. And then we move on to step 4, where we try to find out which CCP has the highest score. So in this case, we're showing that CCP3 had the highest score. So we will add CCP3 to our target CP list and then move to step 5. So if CCP3 is the target CP, there would be some UCPs and other CCPs in its neighborhood. What we do is we prune the trace driver graph by removing all the UCPs in the neighborhood of the target CP, and we also remove the target CP. Once that's done, we move to step 6 and check if one of the exit criteria is met. So for example, it's possible that after pruning all the UCPs, there is no UCPs left anymore, so that would stop the process. If the exit criteria is not met, then we move to step 3 again, where we reassign scores to all the low hit CCPs on the pruned graph. And then we move to step 4, where we figure out what is the CCP with the highest score on the second round of this GraphCov. And we keep doing this process and keep building the target CP list until we hit the exit criteria. And once we hit the exit criteria, then our aim is to bias tests to hit target CP. And for this, we use the BAYOP tool, or sometimes it's also possible to ask TV engineers to give a set of test plus args, which would bias the test towards these target CPs. So here's the final piece of the puzzle. Once we have identified a list of target CPs where we want to bias our test towards, how do we really find a set of knobs which will cause a test to bias towards that target CP? And for this, we use an in-house tool at NVIDIA which uses Bayesian optimization. At a high level idea, what Bayesian optimization does is that it will take inputs, the target CP, and also all the value plus arg and test plus args that are there in the test bench. And then it'll start exploring the exploring the landscape of how the target CP looks as a function of the various value plus args and test plus args. So it'll run batches of tests, learn the function mapping from target CP as a function of these value plus args, use that learning to generate the next batch of targets value and test plus args that it wants to explore, and it's an iterative process, and eventually it spits out the value plus args and test plus args, which boosts the target CP. Although Bayesian optimization is very useful, we found that it cannot really deal with a huge number of test plus and value plus args. So we found also that just asking DV engineers for plus args which can boost the target CP can work also very well. And if the DV engineers can give such a set and they're not sure of the exact values, then Bayesian optimization can work with those limited set of value plus arg and test plus arg. And finally, just wanted to mention that in order for these experiments, which the results of which we're going to present in the next slides, we did not add any plus args to control the test. We would only use existing test plus args and value plus args at the end of the project. So before moving over to the experimental results for GraphCov, I'd like to present at a high level what the runtimes are for this method. So the first step, which is using NPI commands to extract raw data file for the trace driver information, is about an hour for a unit level design at NVIDIA. And then we have a script which parses the raw driver information and the coverage data to generate the color TDG that approximately takes 3 minutes. And then once the color TDG is available, running the GraphCov to find the top targets CPs took us about 5 minutes. So overall, this process took about 1 hour, 8 minutes to identify the list of target CPs. So using the GraphCov algorithm, we identified 3 target CPs for a unit level design at NVIDIA. We then used BAyopt tool to boost the hit rate to those target CP using specific directed knobs, and we ran about 10,000, 5,000, and 4,000 tests for these targets. Overall, about 19,000 tests we ran, and we found that we were able to boost. So for the first target CP, we were able to boost the CP hit per test to 23 times than what was observed at normal end of project report for this target CP. And in this experiment, we found that the number of UCPs that were hit were 7. And interestingly, this biasing was able to hit 6 UCPs in the neighborhood of the target CP. And there was 1 UCP which was hit outside the neighborhood of the target CP. Similarly, for target CP2, after running 5,000 tests, we were able to, using directed knob, we were able to boost the CP per test by 390x. And in this case, the number of UCPs that were hit were 24, and 22 of them belonged to the neighborhood of the target CP, and the 2 were outside. Similarly, for target CP3, we were able to boost the CP hit per test by 20x, and we hit 15 UCPs, and 6 of them belong to the 6 sub neighborhood of the target CP. Combining, we found that in 3 set of experiments, we were able to hit 46 UCPs and wave off 44 UCPs, and the total number of UCPs at the end of the project went down from 609 to 519, which is a 15% reduction, but just running 3 sets of experiments with GraphCov. In conclusion, I'd like to say that GraphCov shows promise in identifying uncovered cover properties which were unhit due to test biasing issues in the test bench. Although we figured out that BAyopt can be very useful in finding the knob combinations because of the inherent limitation of the BAyopt, it cannot handle more than 20 plus args. We cannot fully automate this process of knob selection currently. So future work would be to find out a way which could automatically do this knob selection for a large number of plus args. And finally, although BAYOP shows promise, GraphCov shows promise in hitting the UCPs, it cannot hit uncovered CPs which were not hit due to limitations, inherent limitations in the TB, such as over constraints or inbuilt timing limitations and sequence and so on. Thanks for watching this presentation.